Welcome back to Mastering Algorithms. So far, we have learned the fundamentals, what algorithms are, how to measure their speed using time complexity, and how to analyze the memory they use. Now it's time to start learning real algorithms. We will begin with one of the simplest and most important searching algorithms, linear search. If you have never studied algorithms before, this is the perfect place to start. By end of this video, you will understand how linear search works, how to implement it, where it's useful, and why it becomes slow for large data sets. Let's first understand what searching means. Searching simply means finding a particular piece of information from a collection of data. For example, finding a friend's phone number in your contacts, looking for a product on an e commerce website, searching for a student's roll number, or finding a specific email in your inbox. Every application performs searching in one form or another. The only question is how efficiently can we find what we are looking for? Linear search is exactly what its name suggests. We search through the data in a straight line. We start from the first element. If it's not the one we are looking for, we move to the next, then the next, and we continue until either of the conditions satisfies. We find the target or we reach the end of the array. There is no skipping, no shortcuts. Every element of the array is checked one after another. That's why it's called linear search. Let's understand this visually. Suppose we have this array. Our goal is to find 67. We begin with the first element. Is 12 equal to 67? No. Move to the next. Is 25 equal to 67? No. Then 48. Still no. Now we reach 67. Yes. We stop immediately. Notice something important. We didn't continue checking 81 and 95. As soon as we found the element, we ended the search. Now let's search for 100. We checked 12, no. 25, 48, 67, all no. 81, 95, still no. We have reached the end of the array. That means the element doesn't exist. This is called the worst case for linear search. We had to inspect every single element before reaching a conclusion. Let's write the algorithm in Java. You can use any language. We start a loop from the first element. For each position, we compare the current value with the target. If they match, we immediately return the index. Returning immediately is important because there is no reason to continue searching when we have found our element. If the loop finishes without finding the element, we return -1. In Java, returning -1 is a common way to indicate that the element was not found. This solution is short, easy to understand, and commonly asked in interviews. Let's dry run the code. Initially, I equal to 0. The value is 12. Not a match. Increase I. Now I is 1. The value is 25. Still not a match. Increase I again. Now I is equal to 2. The value at array of I, that is 2, is 48. This matches the target. The function immediately returns index 2. Notice that the algorithm doesn't waste time checking the remaining elements once the answer is found. Let's analyze the performance. The best case happens when the target is the very first element of array. Only one comparison is needed. That's considered O of 1. The worst case happens when the target is the last element or isn't present at all in array. In that situation, we check every element. That's O of n. The average case is also proportional to the size of the array. So it's generally considered O of n. This is why linear search becomes slow for very large data sets. Now let's calculate the space complexity. Do we create another array? No. Do we use recursion? No. We only use a loop variable and a few local variables. Regardless of whether the array has 10 elements or 10 million, the extra memory remains the same. Therefore, space complexity is O of 1 here. Imagine a teacher checking attendance using a printed list that isn't sorted alphabetically. To find one student's name, the teacher starts from the top and checks every name until the correct one is found. If the student is near the end of the list, almost the entire register must be checked. That's exactly how linear search works. Simple, reliable, but not always efficient. So, when should we use linear search? It is a good choice when the data set is small. It's also useful when the data isn't sorted because binary search requires sorted data. It's very easy to implement, making it perfect for beginners and interview questions. However, if you are searching repeatedly through very large data sets, there are much better algorithms available. Let's compare linear search with binary search. Linear search works even when the data isn't sorted. Binary search requires sorted data. Linear search may need to inspect every element. Binary search repeatedly eliminates half of the search space. That's why binary search is much faster for large sorted datasets. In next episode, we will learn exactly how binary search works. Congratulations, you have now learned your first searching algorithm. You know how it works, how to implement it, and how to analyze its time and space complexity. In next episode, we will study binary search, one of the most frequently asked algorithms in coding interviews. If you enjoyed this video, don't forget to like, subscribe, and share it with someone who is starting their DSC journey. Thanks for watching, and I'll see you in next episode.